In this problem, we have a sample of mercury that is being progressively cooled down. We want to make sure in this one that with looks like a little more complicated kind of situation, that we start off by drawing a phase change diagram. And this will allow us to make sure that if a phase change is taking place, that we figure out what type of phase change occurs, and that we make sure that we cover every stage of the transition as this particular sample is being cooled. So I've drawn in my axes, temperature up on the y-axis, time on the x-axis. I then want to put in the key landmarks. In this case, since it's mercury, I'm putting in the boiling point, 357 degrees, and the melting point, negative 39 degrees. I then go back into my problem and I look at where we're starting off at. And this sample of mercury is starting off at a negative 12.8 degrees, which puts him above the melting point. So he's already melted, he's a liquid. And if I cool him down, then I am simply changing the temperature of that liquid until we reach the melting point, which of course is also the freezing point. So my first stage is simply cooling the liquid mercury. As soon as I hit a negative 39 degrees, then of course a phase change is going to take place. As I continue to cool the sample, that liquid mercury is going to solidify. I notice though in my problem that we are going to continue this until we get to a negative 75 degrees. So I actually have a third step where once the mercury is solidified, I continue to cool it and cool it until it gets down to a negative 75 degrees. So in fact, I have three steps in this problem. Step A, I'm cooling the liquid mercury. Step B, I'm solidifying the liquid mercury. And step C, I'm going to take the resulting solid mercury and cool it all the way down to a negative 75 degrees. Step A, since I'm only changing the temperature, I use Q equals mc delta T. I plug in the pertinent information about the mercury, its mass. I looked up the specific heat of mercury. Key thing is in the liquid state, 0.0335. I take the difference in the final and initial temperatures, and I find that in that first step, simply cooling the mercury, that we have removed 227 calories from the mercury. Stage B, I am now going to freeze the mercury, so I'm going to use my formula for freezing, mass times the heat of fusion. The mass is still 259 grams. Notice heat of fusion, even though the value is 2.82, since we're removing heat, I make that a negative value, and we remove 730 calories. Again, this is an exothermic process. 730 calories are removed in solidifying the mercury. Notice my arrow is telling me that that zero is in fact significant. The third step, the resulting solid mercury, we're simply changing the temperature, so we go back to using Q equals mc delta T. Notice, however, since we're in the solid state, the value of the specific heat is a little bit different in the solid state. We take the difference in the temperature, and for that third stage, we removed an extra 308 calories. The question, the problem, though, is we wanted the total energy removed for the entire process. So therefore, the total heat removed is going to be the sum of the energies removed in all three steps, A, B, and C. These are in fact all negative values, of course, because this is an exothermic process. So at the end, of course, I'm going to end up with a negative value. And so for the total process, to take that liquid mercury, to freeze it, and to turn it into a solid and reduce it to negative 75 degrees, 1,226 calories were removed.